Hi, good morning, everyone. My name is Ana Alonso Serrano, and I'm a member of the outreach team of the International Society for Quantum Gravity. And today I have the pleasure to talk with Philipp Höhn about his research and his ideas on the field of quantum gravity. So thanks for accepting our invitation for this talk, first of all. And then I introduce you a little bit. So Philip got the PhD in the University of Utrecht in 2012. And after several international postdoctoral experience, now is honorary associate professor of London College and assistant professor in the Okinawa Institute of Science. So can you please tell us a little bit more on your academic career and the research interest that you have pursued during these years?
Yeah, sure. So hello, everyone. My career path hasn't been really a straight one. So I've taken a route through different communities. So in fact, before I started my PhD, I worked for a year in classical mathematical general relativity. And then during my PhD, I aimed for quantum gravity. I also became a postdoc in quantum gravity later at Perimeter Institute. But during that time, I actually got very much interested also in an informational perspective on physics generally, and in fact deviated a bit into the foundations of quantum theory and a little bit of quantum information. Then I was actually a postdoc at an institute that focuses on the foundations of quantum theory and quantum information. In fact, I worked a bit in that area for a while, and then I kind of returned more towards high energy physics. I was actually part of the Silicon qubit community afterwards. It's basically the holography community. And then, I became a faculty member here in Okinawa. So I've worked on different topics in quantum gravity, starting mostly with canonical quantum gravity or covariant quantum gravity. Now the things I'm doing are sort of approach independent in some sense. I'm focusing at the moment more on kind of tool sets that are applicable to different approaches to quantum gravity. And in any case, the research that I'm currently doing is probably also more focused on regimes that are not exactly what one would call fundamental quantum gravity, but more effective quantum gravity, or maybe semi-classical gravity if you want, so somewhat closer connected to the physics that we know. Initially in my career, I guess I started out more from the fundamental perspective and aims of, starting with a theory that makes some postulates about what the fundamental degrees of freedom are, such as in loops or strings, and then trying to build up the physics that we know from those degrees of freedom. And so in some sense, I guess one can say that if you look at the scale gap in quantum gravity from the Planck scale to the known physics, you have this huge gap. And a fundamental approach is kind of try to bridge that gap from the fundamentals, so from the Planck scale really, and then try to come back to the physics we know. The research that I do kind of does the opposite at the moment. I try to come from the physics we know and then build a bridge the other way. And the good thing is that people work on different topics, and hopefully at some point we can build a bridge that's from two sides that meets in the middle.
Yeah, that's very interesting. And I have several questions, but the first one is why do you think that this all this field of quantum gravity is important, and it's been so hard to deal with it and find a solution and give so many different perspectives? Because as you said, you can go bottom top or top bottom to approach the same problem, and these complementary views seem in some sense also necessary to tackle the problem.
Yeah, that's right. I mean, I think, there's I think it's very good that there's actually different approaches to quantum gravity in the face of the fact that we still don't really understand quantum gravity. I mean, it's such a difficult problem to just put quantum theory and gravity into a consistent framework. I mean, the efforts go back, I guess, 90 years by now. I guess, while we have made a lot of progress in different approaches, and we've understood a lot more, we still don't really understand quantum gravity. I mean, it's just something very difficult when quantum theory is a framework that's usually formulated where you have some input space and time structures that themselves are not quantum. And then we by now know quite well how to formulate quantum theories, also gauge theories, and all the matter degrees of freedom of the standard model in quantum terms. When you then actually include in that picture the space-time degrees of freedom themselves on which the matter degrees of freedom live. So in some sense, you go from a rigid stage on which things happen to a stage that itself becomes part of the subsystems. That's just a very challenging problem. Yeah, given that, okay, we have made progress, but we're still a very long way from really understanding quantum gravity. It is so good that there's different approaches, because imagine all of us worked on the same approach, and then in the end it turned out that that approach is maybe mathematically a consistent one that just happens not to describe our universe. Then that would have been a huge loss of or waste of time and efforts. And nobody can claim that they know what the right approach is. And there's, of course, conflicts or tensions between different approaches. But I think it's important to keep an open mind overall and not turn this into religious wars. And we're still in a very much of an exploratory phase in quantum gravity. And so we have, different communities researching in different areas of this problem. And they're making different progress, and in order to make fundamental progress on quantum gravity, I think it's very important that we also have a communication across these different communities to learn something from what other communities have learned about quantum gravity that might actually also help us in other areas of quantum gravity. And that's why I think also this initiative of the International Society of Quantum Gravity and these recent quantum gravity across approaches conferences are actually quite important. People do need to talk. Cross-fertilization does happen, and it has already happened. I mean, one can notice at times that problems that people have in different approaches turn out to be actually the same in different approaches, and they don't really notice it, or even some of the concepts or tools that they use are actually the same, but they're just phrased in different ways. And then you realize, okay, some of the tools that people use, even in quite different communities, are actually the same.
Yeah, that's I completely agree. And sometimes we need to go a little bit farther from our perspective in daily life to realize what is the implication and the relation to other approaches. And you also mentioned that one of the basic things there is like how you introduce the degrees of freedom into the content, related to the matter content and the degrees of freedom of the theory, how you consider them. And you also have mentioned that you're very interested now in considering the approach from the information perspective. So what is your view on this kind of approach? Which specific problem or ideas or path you are trying to follow?
Yeah, so I mean, okay, I guess I have some overall perspectives on that. I guess I should say that at this moment I'm not working too closely on that approach, but one of the reasons I think an informational approach to questions of the emergence of space-time structures from some more fundamental degrees of freedom is very interesting is that the concept of information is somewhat agnostic to what the precise degrees of freedom are. It's a fairly universal concept, and so as a universal concept, it might help us to actually formulate things in ways that don't depend too much on a specific approach to quantum gravity. Of course, at the end of the day, when you have a fundamental approach, you're making some postulate or some proposal for what the fundamental degrees of freedom are. They will, of course, feed into, they might give you concrete representation for quantum information concepts or information theoretic concepts in such a theory. But at least the hope is that the general picture of trying to understand the emergence of space-time structures from the correlations of some underlying degrees of freedom, that's at least a priori picture that's not so specific to any one of these approaches. I mean, it is in some sense realized in holography. In fact, I mean, that has been the community that has really driven these developments in the last 15 years. But it has also appeared in other communities, in the loops community a little bit, and also beyond that, in fact. So I like these concepts in short because they're in principle, they provide you tool sets that are somewhat more universal and not so approach to specific. And now I guess you come to the question of how is my work related to that? So like directly to this question of emergence of space-time structures, I guess I had some ideas in the past and that I still have in the back of my head that I want to follow on this, but I have not so actively researched on this. But one of the things that we're kind of looking at in my group is questions of that type at a very coarse level, where we study the problem of subsystems in gauge theories and gravity. So when you want to talk about correlations, quantum correlations, as a glue of space-time, so basically gluing different building blocks of space-time together to generate some emergent geometry, you have to talk about what are the subsystems. And you can ask that question of subsystems already even classically at first in gravitational settings. And it turns out that that's not a completely straightforward topic when you have particular types of gauge symmetries, such as so-called diffeomorphism symmetries. That's a gauge symmetry of gravitational theories.
Sorry, so, could I interrupt you for a moment, like if we have people with more general background about what you refer when you are talking about these gauge theories or these diffeomorphisms, if you have I don't know, simple way to see it or some.
Yeah, so yes, I mean, I guess maybe people will know gauge symmetries from electrodynamics, perhaps. Yeah. The concept is that these symmetries change the field configurations of the photon field a priori, for example. It might also matter fields locally in space-time. So they act locally at each space-time point and can change the configuration. They change it everywhere, but how it changes is really completely local. Gravity is completely different in that sense, at least when you look at the full theory. The gauge symmetry there is, okay, what I should say is, of course, gauge symmetry means these changes, they are symmetries of the theory, and as gauge symmetries, that means the changes of configuration are not physical. So I'm changing the state of the system, but in a way that I can actually, the physical states before and after is still the same. The predictions are all the same. And in gravity, the gauge symmetry is a more complicated one. Instead of changing the field configurations locally at a point in space-time, it actually changes them non-locally. So it reshuffles the field configuration, it shuffles it around in the space-time, or you can also think of that as moving space-time points around. And that comes from the idea of general covariance, which basically means that the theory should be independent of choices of coordinates, and coordinates are basically labels of space-time points. But then how I label these space-time points, that shouldn't matter for the predictions of the theory. and basically relabeling space-time points. You can think of, moving these space-time points around. And so and basically these transformations are gauge symmetries in gravity, meaning that these changes of the states are not physical changes. I should actually physically identify those states, and predictions should be invariant under those. But now when I want to think about subsystems in gravity, and I have to take into account that these are gauge symmetries, it means I define my subregion as a subregion of space-time, but then I have to take into account that there are these gauge symmetries that will move that subregion around. And so the subregion is afterwards not where it was before, but now I'm supposed to identify those states. How do I do that in a meaningful way? And there are ways in which you can do that when you define those subregions relative to dynamical reference frames. So these are just in some sense taking serious the idea that in physics, every reference frame that we have in practice, when we do measurements in a laboratory or observations in the universe, we always we use coordinates in the descriptions, but the coordinates are always associated with physical systems, maybe the walls of the laboratory, or something else, location of the Earth in the solar system or something like that. Yeah. And the idea is to basically, so it means that these coordinates are actually associated with dynamical systems, with the Earth or the lab, which itself is a built out of atoms in a physical system, and that you include that into your theory, that picture that actually you should build what are your reference frames out of physical degrees of freedom. It's a very physical picture. And so what you should be doing is defining your localization or your subregion relative to other dynamical degrees of freedom. And it turns out you can do that in such a way that, also the dynamical degrees of freedom relative to which you localize, they will be shuffled around by these gauge transformations, but in such a way that the relation between the subregion and these reference degrees of freedom doesn't change. And in that sense, I can say that the relation between the subregion and the reference degrees of freedom is actually invariant under these symmetries. So that gives me a way of thinking about or defining subregions in a physical way that are gauge invariant, that are invariant under these symmetries. And then when you have such a notion of subsystems, then you can start talking about correlations between such subsystems, or thermodynamic interactions and those kinds of things. And so knowing what subsystems are and how we define them, that's of course the absolute crucial thing for talking about correlations in the first place. Without that, we can't do it. And in gravity, it turns out that in any case, if I want to talk about correlations that are also consistent with these gauge symmetries, so that are invariant under moving degrees of freedom around, you actually also have to define them in relative to reference degrees of freedom. And but then you can start thinking about, sort of gluing subregions together via correlations, and where the correlations in some sense, where this entanglement, quantum entanglement, acts like a glue between subregions. These subregions happen we can start by thinking about them classically. So they're kind of big subregions, if you want. They're not fundamental quantum building blocks. But you can still ask at this very coarse level, how to glue such larger building blocks or effective building blocks of space-time at subregions, how to build it together to build a global piece of space-time using correlations, for example. And that's at that level, that's something that we do look at, actually. It's not very fundamental, but the hope is that from this, we can already learn something even about more fundamental degrees of freedom, that this general picture of gluing building blocks together to build larger geometries, that's something that would also hold at smaller scales, for example.
Okay, so I have a couple of questions. So the first one is so you define these subregions of the space-time, and then you to fit to the symmetries that you use and define to move these subregions, you need to define a new concept of reference frames than the usual one that was standard in the physics that we learn at the university, isn't it? And these kind of reference frames are quantum in nature in some sense, isn't it?
Yeah, so I mean, well, they're quantum in nature. If everything is quantum, then yes. So I mean, you can think about these dynamical reference frames also classically in general relativity or in classical field theories, or even in mechanics if you want. I mean, they're a very general concept. Whenever you have some dynamical system with some symmetry, then you can build dynamical frames with respect to that symmetry. And you can do that in the quantum theory also. But yeah, the conceptual step compared to what we learn in textbook theories is that, yeah, in standard settings, we always consider the reference frames to be something external to the system that we're trying to describe. And in particular, it's something classical. So, and the conceptual leap that we're making here is that now all of a sudden, what are the reference frames, or what we can use as degrees of freedom to build reference frames? They're not external anymore. They're not external to the description of the physical system that we want to build. They're actually part of the physical system. They're a subsystem, in essence, of the physical system we aim to describe. And in particular, we can pick different subsystems of such a composite system to act as a reference for the others. And so, but then that means in particular that they're dynamical. And if that total system happens to be described by a quantum theory, then they're also going to be quantum degrees of freedom. And that means that these reference frames are actually so-called quantum reference frames. They're quantum systems with which we associate reference degrees of freedom that we use relative to which we localize other degrees of freedom or describe other degrees of freedom. But because we can have different such subsystems that may act as a reference frame, the total system is quantum, they may be correlated or entangled with other degrees of freedom, they may be in superposition and so on. So it's a much more general notion of reference frame, and a much more, in some sense, more complicated notion. And then you can ask questions, what does it actually mean to describe physics relative to a quantum system? So to jump into the perspective, if you want, of a quantum system and describe the world relative to it. So, and if I can do that with respect to one, can I also find ways, consistent ways to jump into the perspective of another quantum subsystem that relative to the first may be entangled with other degrees of freedom or in superposition or, or whatever. So, and it turns out you can actually do that. And it's, and that gives you a more general notion of reference frame covariance that gives you a novel way of extending the relativity principle into a quantum realm. So when I say that, one needs to be a bit careful because there is of course a sense in which the relativity principle has already long been implemented in the quantum realm, and that's just, for example, standard textbook quantum mechanics or standard textbook quantum field theory, where we're given some quantum system like a quantum field in Minkowski space, and we describe it relative to external to the quantum fields. Inertial observers, some Lorentz frames, and these theories are Lorentz covariant. So the special covariance is implemented in those, but it's implemented in a sort of external way. We do have, of course, these external frame transformations of the Lorentz frames, and we can implement then basically, if I know how one external Lorentz frame sees the quantum field, I can, there's a unitary transformation that tells me, that implements the Lorentz transformation on the quantum field and describes to me how that quantum field will be seen by the other Lorentz frame. So in that sense, reference frame transformations are part of the formalism, but really they're just an implementation of classical reference frame transformations in the quantum formalism, because the frames remain classical and they're external to the systems that I'm describing. And the conceptual leap and also technical step that has happened with quantum reference frames is that now we have more general reference frame transformations that even work for, when I internalize the reference frames and their quantum systems. That's a new development. So.
I see. And what you mentioned before about this way of seeing quantum gravity from an effective point of view, you mean like the phenomenology emergence from the interaction of these subregions that can include some different correlations and between them and the degrees of freedom, and from that kind of building block you emerge an effective theory or an effective phenomenology, and is where you expect to get some new hints about what is the fundamental theory of
Yeah, the question at this moment is not so much of looking at, for instance, gluing these sub-regions together, of then using that to guess what the fundamental degrees of freedom are. It's more to understand such a gluing process in a relatively controlled regime, so a regime of physics and space-time physics that we know reasonably well, and that's close to, to the known physics. And but to get some understanding of how you can do that gluing in a consistent way to then build up a larger space-time structure. And the hope is that, in some sense, gluing building blocks together to form emergent space-time or larger space-time structures, that works more universally, in some sense, independent of the scale you're looking at.
Now, having an idea of the framework you define and how you move the sub-regions and the relations, in that kind of relations, how you define your observables and your clocks for the theory?
Yeah, so indeed, I mean, that's one of the core questions in gravity. What are observables? Observables in the sense of quantities, physical quantities that are at least in principle measurable in experiments, or observable in the sense of observations in the universe, because of course in gravity many of the observables are actually rather related to observations, like in cosmology. And that has to do with that gauge symmetry that I was talking about before, so-called diffeomorphism symmetry that moves space-time points around or reshuffles the field configurations in space-time. So the observables, the measurable quantities, as I said, I should identify the states before I start moving around the field configurations, so space-time points, and afterwards, when this transformation is such a gauge transformation. And that means that observable quantities, they cannot depend on whether I evaluate them in the states before I do that transformation or whether I do that afterwards. So these observables, these measurable quantities, they have to be invariant under this reshuffling of points. And now I can reshuffle these points in really complicated ways, and in very non-local ways. I can take space-time and take the points from one region and move them very far away to somewhere else in the space-time. And now the statement is physics doesn't depend on that, and physical quantities should be invariant under that. So at first that might seem quite mind-boggling. How can I move things in the universe from one place to another, and that doesn't matter? But that just means that these different states before and after, they're in some sense just different coordinate descriptions of the same physics. And I've just moved, just relabeled things. That's all I've done. But yeah, building these observables, it is a somewhat challenging problem in gravity because of those non-local transformations. And okay, I mean, at least formally, you can write down such observables or quantities that are invariant under such transformations fairly easily. But if you want to do that actually explicitly for calculations, that can be a pretty difficult problem because because the flows or these symmetries under which they have to be invariant, they can have a very complicated action, and it's an infinite dimensional group under which they have to be invariant. So it's also technically very complicated. But what I can say is that's how you build those observables is exactly related to those dynamical reference frames that I was talking about before. As I mentioned, you can define a subregion relative to a dynamical reference frame, and then the relation between the subregion and that dynamic reference frame is invariant under moving around the field configurations. They both move around, but in a way that their relation isn't changed. You can think of that in analogy to, suppose I have two particles on a line, and the symmetry or the gauge symmetry is that the physics has to be invariant under global translations. I can take the two particles, they have a relative distance. If I move both of them together globally, the relative distance doesn't change. So, and basically we do something similar, but now for a much more complicated symmetry. And with these two particles, you could say one of the particles is a reference for the other. I'm localizing the second particle relative to the first, and I describe its location in terms of the relative distance to the first. And so in some sense, what we do in gravity is similar to that. We're describing some physical quantities we might be interested in relative to such a dynamical frame. And just like the relative distance is invariant under these global translations, in the gravity case, such relations remain invariant under such complicated transformations. And it turns out that actually people in different communities in gravity have actually thought about the same problem, of course, because when you have that gauge symmetry, and everybody knows that you have to, in some way, build observables that are independent under these transformations or invariant under these transformations. And so in different communities, people have started building formalisms or tools to build such observables. They have different names, and in one community they call them dressed observables, in other communities they call them relational observables. And there exist many different formalisms for them. But the interesting thing is, at the end of the day, you can actually show that they're all consistent with one another. They're just different formulations of describing gravitational observables. But the core concept in relating them is really dynamical frames. So you can build descriptions relative to dynamical frames, and then you can see that all these previous methods for building diffeomorphic or gauge invariant observables in gravity can be formulated in that way. And I think this is physically quite nice, because it's not just some abstract formalism, but there's conceptually some nice ideas inside. What I already mentioned earlier at some point, that, you know, in reality or in practice, all the reference frames or coordinates that we use in actual measurements or observations, they are related to physical systems. They're attached to physical systems, and that's really just a way of phrasing it. And basically the theory just tells you that relations between systems, that's what's physical. But having some external non-dynamical reference frames in gravity is not something that actually is physical. And that's basically one of the core messages of general relativity, that physics is actually about relations of systems, and this is in fact not something that is often taught directly in general relativity in courses. That's something that one starts realizing or learning afterwards.
And just a final question regarding something you mentioned at the beginning of the conversation, that you were interested for long in the foundations of quantum physics. So what's your approach to that? So what are you trying to tackle, to understand the interpretations, to go beyond what we have learned in the textbooks in university? And what?
Yeah, so in some sense, it was the aim when I was starting with that was to actually make sense of the textbook formalism in terms of, you know, these big debates about interpretations of quantum mechanics. What does it actually tell us about nature? What I should say is, when I started thinking about foundations of quantum theory, and in particular the aim was to understand the formalism of quantum theory from an informational perspective. And that was initially meant to be sort of a warm-up problem to a bigger problem, because I was initially motivated to understand space-time structure from an informational point of view. And but then before I went into that, I thought it would be an easier problem to first of all understand quantum theory from an informational point of view. And basically, so that's how it was a bit of an accident that I went into the foundations of quantum theory, basically through motivation from high energy physics. And but yeah, in some sense, the motivation became, we have this beautiful theory. It's mathematically beautiful that you learn in textbooks, but in many ways that theory also drops a bit from the sky. So we have a bunch of textbook axioms that states are rays in a Hilbert space. Time evolution is some unitary transformation. Composite systems are given by tensor product structures, and so on and so on. And okay, we need to have complex Hilbert spaces rather than Hilbert spaces over the real numbers, and so on and so on. You can ask the question, why? Why should the quantum formalism be actually formulated, or why should nature be described in terms of such mathematical axioms? And the key difference between quantum mechanics and maybe relativity theory, both special and general relativity, is in many ways that the theory of special relativity or general relativity is often, it starts from very physical axioms about the relativity principles. The laws of physics should be the same in every reference frame, and maybe in gravity also the equivalence principle. So these are things that give one some physical intuition, and from there one starts building up a theory that helps very much in interpreting what the theory tells us. And for instance, in special relativity, of course, it had also a lot of counterintuitive phenomena that come from it, such as a relativity of simultaneity and time dilation, Lorentz contractions, and whatnot. But it just happens to follow from basically the relativity principle that all the laws of physics are the same in every frame, inertial frame, and in particular that the laws of electromagnetics are the same in every frame, and so in particular the speed of light is the same in every frame. So you can't distinguish different inertial frames by the speed of light that they see, and that's a very acceptable axiom. But when you start with that, then you will realize that actually, if I accept that, then I also have to accept that I get the relativity of simultaneity and time dilations that seem very counterintuitive at first. And in particular, I can even argue for these things without writing down equations, really. I mean, one can even just by conceptual arguments realize that that's true. And so that's, of course, one of the main reasons why in special relativity, or also in general relativity, has never been such a huge debate about the meaning of the theory in contrast to quantum mechanics. And quantum mechanics does not, in textbook quantum mechanics, does not start from physical axioms. It basically starts from, here's a bunch of mathematical axioms, and you have to accept them. One can motivate them, and to some degree, it is true, but they're not really derived from anything, and at least not in the usual textbook formulation. And okay, you can accept them. You get a theory that just works beautifully. It describes basically every measurement where quantum physics is relevant accurately. So somehow the world is described by that framework. But then you can start asking why, and can we maybe, similar to relativity theory, formulate some physical principles from which we can actually derive the formalism of quantum theory? And if so, would that also help us in maybe settling, or maybe at least relieving somewhat the debates about the meaning of the quantum formalism? And those ideas go back to some people. In fact, when it comes to thinking or suggesting that one should do a reconstruction program, that actually goes back to also a quantum gravity person, Carlo Rovelli from Loop Quantum Gravity. He wrote a very influential paper on so-called relational quantum mechanics. that's actually a suggested interpretation of quantum mechanics, but in it he also suggests to do a reconstruction. It was then also independently proposed by Anton Zeilinger, for example, that one should do something like this, and by a couple of other people. And then in the early 2000s, a wave started working on this program that started with Lucian Hardy from Perimeter Institute, and then after that, there were a bunch of successful reconstructions of quantum mechanics from different principles. Let me just say different principles at this moment. Whether they're really physical, one can debate about some of those. But the point is, what does it actually mean to do a reconstruction of the quantum formalism? It means we actually have to go to beyond the quantum formalism, right? So it's the theory we want to isolate using some physical axioms. So we have to go to some kind of landscape of alternative theories. So theories, how the world could have been if maybe some other, physical laws were actually were applicable to our world. So one example is classical physics, of course, or classical probability theory, or even you can think of quantum mechanics with real Hilbert spaces or quaternionic Hilbert spaces and so on. But you can have a whole continuum of theories that make up a landscape. And so what you have to develop is somehow a framework that gives you a description of how to describe physical systems that applies to every theory in the landscape. And then within that landscape, so in particular, you have to find a formulation that in the end will apply to quantum theory, but doesn't assume anything about complex numbers a priori, about Hilbert spaces, Hermitian operators, and so on and so on. And that's something we want to recover in the end. And there exist ways in which you can do it. And then you have a theory of a landscape of theories, and you want to now find physical principles that make sense within the structures of that landscape that I can formulate also in a mathematical way, but that also have some physical meaning. And that just happened to be, in some sense, the coordinates of quantum mechanics in that landscape, so that are, in some sense, the axioms that isolate quantum mechanics in that landscape. And so I've also worked in that program and developed one of those reconstructions with a collaborator. And but there's also a number of other reconstructions, successful reconstructions. Most of them are actually for, I should say, finite dimensional quantum mechanics. And it is possible to derive quantum theory from somewhat informational axioms that are telling, that are, in our case, they're rules that constrain how an observer can acquire information about subsystems that they're basically measuring. And so that does give you, of course, a new perspective on quantum mechanics. Now, coming back to the core question, does it settle the question of its interpretation? And the answer is it doesn't. It gives some, it kind of singles out, in some sense, a partial interpretation of the quantum formalism, in the sense of it is somehow about information. It's somehow a rule book or a law book about, how you acquire information about physical systems and how you should reason about the world. But it doesn't actually tell you what exactly that information is that you're working with. In particular, in the foundations of quantum theory, there are always these questions whether we can recover quantum mechanics from an underlying theory that has more variables, so-called hidden variables. Is there some hidden information, and does it emerge from that or not? And that question is not settled by it. In this reconstruction, it just happens that we never need to talk about any hidden variables. We're just not mentioning them at all. You don't need to talk about them, and they're not necessary to recover the quantum formalism. But by not talking about them, it doesn't mean that maybe you cannot. I mean, that you could, of course, also formulate the axioms that we have then phrased in order to recover the quantum formalism in terms of hidden variables or something like this, and that the information one is talking about could be phrased in terms of hidden variables. So that's the reason why, at the end of the day, it doesn't actually settle that question. And
yeah, all of this is so interesting that I think that we could keep on talking and asking questions for a long, but I don't want to extend so much. Also, something that you said that I think a lot of us can relate to is that sometimes you try to focus in a simple issue that you want to understand and you think is simple, direct, and a warm up, and you keep on digging and you end up like it drives you to a different whole topic.
Oh yeah.
And
So I
it
mean,
is so
actually,
interesting.
when I started this, like I said, I thought it would be a simpler problem, but in the end, it took several years to actually
So, and that leads
finish
me to
that reconstruction.
the final question that I want to ask you for the audience, and it's like, what was your, I don't know, why you were first attracted to this field, and what you would say to a young student that wants to start, I don't know, trying to understanding these simple questions at the beginning?
Sorry, how was attracted to this general field of fundamental physics, or foundations of quantum theory?
Both. I don't know what you
Both.
prefer to.
Yeah, okay. So I mean, fundamental physics, that actually happened. There was a phase transition in high school. So we had, standard physics was, Newtonian mechanics, balls rolling down an incline and so on. And okay, I was never amazingly interested in that. I should say. I mean, one could treat these things, but then at some point we had kind of a dessert session in 10th grade for physics, and we covered, I think, in 1 or 2 weeks special relativity, and so that's when I learned about time dilation and Lorentz contractions and those kinds of things, and for me the most amazing thing was that and something like the relativity principle, that, or the observation that you can start from some very basic, in some sense even philosophical or conceptual principles, such as the relativity principle that all the laws of physics should be the same in every frame or every inertial frame, that you can make predictions just in your head, basically, that then turn out to be true, that you can actually go out and measure, and then you find confirmation of that. And so in the sense that you can just by thought power, make predictions about physical effects that are measurable. That was a very deep observation for me that triggered me so much that at that moment it was clear that I was going to go into fundamental theoretical physics. And in fact, before I even studied physics, I already knew that I wanted to go into quantum gravity. And so here I am. But so in that sense, it has been a long time coming. But in fact, I was also, even before I started studying, very intrigued by the problem of time, actually, or what time is. And then for a long time during my studies, I kind of lost a little bit of connection to that. I wasn't really thinking so much about it. But then during my PhD, I started working actually also on the problem of time, and I've continued working on that in recent years. So, but that wasn't really so much planned that I would come back to it. It just somehow happened. But yeah, it's some of the things seem to have been coming a long time, and but then when it comes to things like the foundations of quantum mechanics, or some of these questions, they just grow out of curiosity, I'm interested in fundamental physics or in understanding physics, and sometimes the more you learn about something new, you realize, okay, there's really, really interesting questions there, and then you spend some time, you really want to know the answer to something, and that's really how it usually has worked for me. Yeah.
Okay, so, and thank you very much for your time and accepting the interview, and it was a pleasure to talk to you. So I hope all the audience enjoy the same that I enjoy listening
yes.
this. So thank you.
Yeah, thank you very much.